Today, we will be thoroughly discussing the concept of quantile regression, specifically focusing on its practical application within our time series lecture.
All right, let's get started with the fundamental principles.
The OLS, which stands for ordinary least squares, will simply examine and determine how the independent variable x will affect the dependent variable y, specifically focusing on the average impact. So, the primary question this method addresses is, what exactly happens on average?
The quantile regression, in its very essence, actually addresses a fundamentally distinct question. What exactly happens to the specific quantile distribution, or perhaps the percentile distribution of the variable in question?
For example, we need to understand how x, our primary regressor or explanatory variable, might specifically influence the overall distribution of y. More precisely, how does it affect the lower extreme of the tail in contrast to the central part or the upper end of its range?
So we're not simply targeting the average value of y. Instead, we are specifically aiming for a particular percentile within the y distribution, and our entire analysis is focused precisely on that specific part.
The quantile regression will become quite useful and particularly handy if we want to thoroughly examine and understand how the independent variables or regressors truly affect the dependent variable y, especially when we're looking at what we call bad states, which means that the y value is quite low as opposed to when it's in more normal or typical states.
So for instance, if we are dealing with a y variable, such as the rate of return, then the primary inquiry often revolves around how the x variable might potentially influence or impact it. The return in a crisis or bad states where the average return is low versus how these regressors affect the y, the return in good states.
So, considering this specific situation, we can now...
Our analysis aims to thoroughly reveal the complex and varied impacts that x has on y. For the sake of making the discussion concrete, let's consider a scenario where we conduct this specific quantile regression analysis, with our primary focus directed towards the 10th percentile of the distribution. And in this particular model, we are working with just a single independent variable, x. Once we have completed the estimation process for this quantile regression model, we find that the estimated coefficient, specifically beta 1, turns out to be exactly 1.5. This indicates that the 10th percentile of the conditional distribution moves upward by 1.5 units, implying that if we consider this y variable's distribution, and this specific numerical value will then be established as the official cutoff point for the 10th percentile. So minus 0.5, for example, or below, all these values will make the lowest 10th percentile of the y variable distribution. Now, if the variable x occurs and its value increases by a single unit, then the entire y distribution, specifically its cutoff point, will consequently shift towards the right. So in this specific instance, we're going to see a significant increase from a value of -5 to a value of -3.5. So the 10th percentile, or the 10% distribution on the left side of the y-axis, will shift to the right. So the original cutoff point, which was -5 before the increase in x, will now become -3.5. So if we consider a scenario where our variable x increases by just 1 unit, then the 10th, the tau conditional quantile of y, will experience a change that is precisely quantified by the coefficient beta 1. What this essentially means, in more practical terms, is that those very negative or bad outcomes have now become noticeably less severe. The initial reading indicated a value of -5, or perhaps even less than that. However, the critical cutoff point has now been elevated, indicating that the previously very severe outcome has become considerably less dire with the introduction of factor x. Consequently, the lowest tail of the statistical distribution no longer extends as far to the left as it did previously. To put it another way, if the value at the 10th percentile of the distribution rises from a -5 to a -3.5, specifically when the variable x increases, then we can conclude that the lower tail of the distribution for y shows a clear improvement. The threshold below which the worst 10% of outcomes lie becomes less negative. This particular observation suggests a noticeable rightward improvement within the left tail of the data. However, by itself, this does not definitively prove that the entire distribution has been shifted in a uniform manner. So what we are doing here is specifically focusing our analysis on a certain segment of the y distribution. So, for example, in this situation, if the quantile regression beta, we observed that at the 10th percentile quantile, the value we found was 2. Now, if we were to repeat this entire regression analysis using precisely the same independent x variable and naturally the very same dependent y variable, but instead we focus our attention on the 90% quantile. And if the beta value is different, for example 0.5, it indicates that the predictor has a much stronger effect within the lower tail because the coefficient here is higher compared to the upper tail.
This indicates that the predictor holds greater importance during difficult periods compared to more favorable or prosperous times. This clearly demonstrates a heterogeneous impact from X, meaning its effect isn't constant across the different levels of the Y values. And in this particular case, it becomes quite important to perform the quantile regression analysis specifically to fully uncover the diverse and heterogeneous impact that X has upon Y. But how exactly does the optimization process work when we're trying to find the quantile regression coefficient? Just to give you a quick reminder, the ordinary least squares method, or OLS, operates in a specific way. Its primary goal is to identify the optimal beta coefficient, ensuring that it effectively minimizes the sum of the squared errors. So the idea here is that we need to have the best fit model. So that fit model
We will draw a line where the error is precisely located. It is possible to make it as small as possible.
So the OLS approach essentially involves minimizing the value of the squared error term. The reason that we square the error is precisely because by its very definition, and as a default consequence, when we feed a line right in the middle, we are inevitably going to have both positive errors and also negative errors. We simply cannot operate with these differing signs of errors because they will ultimately cancel each other out.
This is precisely the reason why we choose to square the differences. Once we have squared these differences, our next step is to then minimize that resulting squared error term. This fundamental approach is exactly how the ordinary least squares method typically performs its calculations. But then, how exactly does quantile regression manage to accomplish this task and ultimately provide us with its unique beta coefficient values?
It's not quite as straightforward as some might mistakenly assume, where we simply identify the absolute lowest Y value within our dataset and then proceed to apply a standard ordinary least squares regression model to it. Such an approach, quite frankly, is fundamentally flawed and simply won't yield accurate or meaningful results. Instead, the more robust and appropriate statistical method, known as quantile regression, is specifically designed to effectively handle this type of analysis, ultimately providing us with a much more nuanced and insightful outcome.
By introducing a specifically different weighting value for the error.
So for the ordinary least squares method, due to its inherent nature, specifically because we are performing a squaring operation on the differences, it inherently places a greater penalty on those larger residual values. This is because when these larger residuals are squared, they will contribute much more significantly to the overall sum of squares, or the error term. The magnitude of the error, that is, and the extent of the deviation, will be heavily penalized and directly addressed by the ordinary least squares regression model. When considering the quantile, specifically the Quantile Regression approach, we intend to apply distinct weights to the error. These weights will vary according to the particular quantile or percentile selected for the quantile regression analysis. So, in this instance, we're addressing the very same idea. We're simply determining the error term. So, this first point that you see here, this is what we refer to as the actual Y value. And then right next to it, we have what's known as the fitted or the predicted Y value, which comes from our model. Consequently, what we're calculating here is simply the difference between that actual Y value and the predicted one, often denoted as Y hat. And this operation will precisely give us our error term. However, instead of giving them equal weight, we'll weigh them by this. That will give us the penalty.
It depends on the percentile that has been selected. For example, if our focus is on the lowest 10% of the distribution, then we would like the regression to focus on
Fitting the predicted value, which is low. So in the event that the predicted value turns out to be low, it is most probable
It is quite probable that the Y value will be observed to be higher, and as a direct consequence of this, the error term, which is precisely calculated by taking the actual observed value and subtracting the predicted one from it, will then be positive. A positive error indicates that our predictions are consistently falling below the actual observed values. This implies that we are specifically aiming to capture the lower end of the data distribution, which is desirable if our quantile regression model is designed to target the 10th percentile. In this particular scenario, the assigned weight for this error will be quite low. It's going to be multiplied by a factor of 0.1. So the penalty assigned for this particular error is kept quite low because our objective is to encourage the regression model to primarily focus on that lowest 10%. However, if the error, for example, Let's consider a situation where the error, the predicted value, is quite high. And in fact, it's even higher than the actual observed one. So in this particular case,
The error term would be b minus that value.
because at this point, the predicted value is considerably higher when compared to the actual observed outcome. And under these specific circumstances, we then proceed to assign a much larger penalty. This penalty is calculated as 1 minus the value of 0.1, which in this particular scenario results in a value of minus 9. Take a look at the weighting we have here, which essentially defines the penalty value, or what we call the loss function, is quite distinct in this case. Since our primary focus is specifically on the lowest 10 percentile of the data, we therefore encourage the regression model to exhibit a positive error, meaning it should slightly overestimate or
Under prediction, which is a situation where the predicted value of y is lower than the actual one.
Therefore, we decided to assign a lower weighting to this particular aspect, simply because we find it more desirable. However, if the actual observed value happens to be significantly less than the value that was initially predicted, this clearly indicates that our system is consistently overpredicting. This implies we're aiming to reach this specific point, and this isn't ideal for us, as our primary objective is to concentrate on that crucial lowest 10 percentile, specifically that lowest 10%. Consequently, under these circumstances, we will need to impose a significantly heavier penalty. And that's the entire process. After we've located the specific error, we then assign weights to them, and subsequently we determine the optimal beta value that will effectively minimize the overall error. The beta parameter that minimizes the error will simply be the solution for our quantile regression analysis. Let's consider, for instance, this particular situation. Suppose we're dealing with a set of y values, and we're performing a simple regression analysis. In this specific scenario, our objective is to fit only an intercept term, nothing more than a basic intercept. There are no additional regressors involved, meaning we don't have a beta 1 coefficient. It's solely a beta 0, or perhaps a constant c exactly, just an intercept. If we are attempting to determine the median regression, which is essentially the 50th percentile within the framework of quantile regression, then it becomes quite clear that we already understand the answer to be 7. Because the number 7 in this particular context appears to be the central value, the one positioned right in the middle of our conceptual framework here. And this is something we are fully capable of verifying through further examination. So our initial step involves finding the error. This error is defined as y, from which we subtract the predicted value, which is represented by c. For instance, if we subtract 2 from 7, the resulting error would be minus 4. Let's consider a scenario where c is set to 4. We begin with the c value of 4, even though it's not the accurate one. But if we proceed with c being 4, then we're going to observe these resulting errors. Specifically, we'll see 2 minus 4, followed by 4 minus 4, and then 7 minus 4. This calculation is simply the actual y value minus the corresponding predicted value. For instance, 10 minus 4, and so on. And then we take the absolute value of that. We don't square these values because in this particular context, we are specifically discussing the median regression, which is a special case where the percentile value is exactly 0.5.
In this particular situation, we are not concerned with whether the deviation is on the positive or negative side, as our objective is to hit the precise center point.
So we don't have a penalty assigned here. We just find the error, take the absolute value. We have to, because we don't want the errors to cancel each other out.
And then we find the error term. Is this truly the best solution? Of course not, because if we assume a different solution, for instance, a constant that equals 7, and then we find the error, which is the difference between the y and the c value selected, in this specific case 7, then the error will be lower. But if you select 10, the error will be higher. So that particular option would probably be the very best solution. However, what if your specific requirement is to obtain the 25th percentile? So we can then proceed to examine a range of different possibilities. Specifically, let's take the example of 4, which we've identified as being the correct and accurate solution. And this is fundamentally due to the fact that the 25th percentile corresponds exactly to this particular value. That will be the cutoff for the lowest 25% of the y values distribution. Therefore, if we were to set the value of c to 4, we would then be able to quite easily identify the resulting error. Specifically, it's the y value minus 4 for every single individual case, and as a result, we are consistently observing these particular errors. Now, considering the fact that our objective is to target when we are considering the lower part of the distribution, we then prefer to have underproduction rather than overproduction. This essentially means that we would rather have a low predicted y value. In this situation, if we find ourselves with a positive numerical result, that will certainly be the one we prefer. So, any positive error, meaning overproduction, will receive a much lower weight. To clarify, we'll apply reduced weighting because our preference is strongly for underproduction, given that our objective is to target this particular area.
Any error that is positive, meaning we find ourselves in this particular situation, will result in a significantly lower penalty, specifically 0.25.
It is simply not possible for us to completely eliminate the penalty in this specific instance. This is primarily because our designated target value, the one we are aiming for, is precisely 0.25. Consequently, a certain degree of penalty will inevitably be incurred. However, this particular penalty will be substantially reduced, significantly smaller than if we were consistently overpredicting the y variable.
So, considering this specific situation, these values that represent underproduction and have resulted in a positive error will now be adjusted by a factor of 0.25. We then proceed to multiply them by this same 0.25, and that gives us the final outcome here. When the actual value is less than our prediction, it indicates that we have overpredicted. This outcome is certainly not what we desire. Therefore, we will apply a significantly higher penalty, specifically a factor of 0.75, and this will then contribute to our total error calculation.
Now, this particular method of applying this kind of weighting will essentially compel us to favor this specific solution, because this solution, as you can clearly observe, actually possesses numerous values of errors that are associated with a significantly lower weight when compared, for instance, with the case where c is equal to 7.
When the value is 7, we generally find it's 0.75 or even greater than 7.
Therefore, this approach ought to be considered the optimal solution, as it is designed to yield the absolute lowest possible error rate. To ensure a solution prioritizes this specific aspect, we intentionally assign a distinct penalty value whenever an error occurs.
Now, if we take another example, the core idea remains the same.
If we have a regressor, and let's consider this regressor's behavior as it unfolds over time, and we also have our corresponding y value, the fundamental concept, the core idea, is to find and explore a variety of distinct and potentially viable solutions.
Isa, we have the constant term, which is beta 0, and then we have the slope, which is represented by beta 1. So these are our two key parameters, beta 0 and beta 1. Given this, we're presented with various different possibilities. Ultimately, our goal is to determine the best fitting line.
This approach is designed to effectively minimize the overall error. So when we are specifically discussing the median regression model, the particular line that will consistently provide the absolute lowest error is clearly line A.
In comparison with
However, if you want to find the quantile regression focusing on the 10th percentile, the 10th quantile regression, then the solution will be different. As we've discussed previously, the lowest distribution is going to prefer to show a positive error because that specifically will indicate underproduction, and that is the exact situation that we would prefer.
Consequently, these particular types of errors are going to be given a considerably reduced significance when compared to the singular negative outcome. The negative aspect concerns overproduction. If you apply the identical process, identifying the error after carefully weighting each one by its specific penalty, then the resulting solution will consistently provide us with the optimal line. In this particular instance, it will clearly be line A, and so forth. Now, we will proceed to apply this particular concept by making use of the Finance Research Guide. I'll proceed to select the time category.
Right, the next step is to make sure we select the monthly frequency covering the entire period from the year 2000 through to 2024.
First, you'll want to go ahead and click on the Apply button. And then, following that, we will proceed to select the appropriate X variable from the list.
The standard deviation.
So what we have here is the standard deviation of the daily returns, and that will be just one single number for any particular month. So for each month, we take the daily returns and then we compute their standard deviation. This gives us a clear monthly figure that shows the volatility of the returns, which is carefully constructed from the individual daily observations.
Okay, so this particular value here is our monthly volatility measure. We're going to designate this as our independent X variable, and subsequently our objective will be to thoroughly examine the impact of this X variable on the overall return, which of course serves as our dependent Y variable. Now, in the context of this specific example, we're going to apply this principle to just a single firm. To illustrate, let's randomly select a company, for instance Apple, and after that we'll simply click the Apply button.
Following that, for the second phase designated as Series B, our objective will be to commence the construction of the Y variable.
The return that we get each month.
Of course, it's absolutely necessary for us to pick the exact same company, and that's Apple. And then the next step is to simply click on Apply Filters. Once we have successfully constructed both the x variable and the y variable, we can then proceed to take a brief look at the visual representation of the scatter plot showing y in relation to x. The variable y is what we expect to be returned as the output. However, it is quite essential that we must patiently hold off before we can begin to initiate this specific kind of chart. All right, so for our x variable, that's absolutely correct. We're talking about the standard deviation of the daily return, which is essentially the volatility of the asset. And then for y, that's simply the monthly return. Yes, that's right. Now, if we proceed to examine the relationship between these two variables, y and x, it's evident that the quantile regression technique will be quite advantageous. It will be quite beneficial because if we take into account those larger values, specifically the y values that are positioned above the average, by examining these particular data points, we are able to discern a clear and definite positive relationship. We can observe a clearly defined positive relationship in this context. However, if we examine the y values that fall significantly below the established average, then we would expect to perceive a distinctly negative correlation instead. As that increases, we typically observe a corresponding decrease in y. This particular pattern applies when the quantile falls below 0.5. Conversely, if the quantile is found to be above 0.5, then greater values of y suggest a clear positive relationship. It's quite clear to us, we can discern this. Therefore, it's imperative that we thoroughly test this key assumption by performing the necessary statistical procedure, which is a quantile regression. So, the dependent variable, which we're calling y, represents the monthly return, and then the independent variable, which is also referred to as the exogenous variable, or sometimes the regressor, or even just the x variable, that is the volatility. And then at this stage, it becomes necessary to select the specific quantile. Okay, so first we'll begin by setting up the point one quantile regression model. Once that's properly configured and fitted, we'll then proceed to execute the regression analysis. This step will require a moment or two for the system to fully process the data and generate the results.
And here we have the definitive result. Exactly as predicted when we observe low values for y, specifically those falling within the lowest 10th percentile of the distribution, we find that the x variable exhibits a negative effect. This outcome is entirely consistent with the predictions made by the previous figure and is considered statistically significant. If we were to increase this value, perhaps from a starting point of 1 all the way up to a value of 5, considering a statistical analysis known as median regression, we would then proceed to execute the regression analysis once more. We're still seeing a negative result here, but it's an improvement compared to our previous measurements. Although we're still in the red, the situation is better. Our ambitious goal is to reach the 90 percentile, aiming for top performance. And then we proceed to fit the regression model, which means our aim is to specifically target the underlying relationship between y and x. So if y exhibits particularly high values, specifically those in the top 90 percentile of all values, and then the relationship eventually turned out to be quite positive and significant. So we can now summarize the main findings here. The lower tail regression, specifically at the 10th percentile, showed that the coefficient was indeed negative and statistically significant. This indicates that an increase in return volatility significantly extends the lower tail of monthly stock returns, meaning that in periods when Apple is performing poorly, this volatility will amplify that negative performance.
So it's like we're experiencing bad volatility.
However, if Apple's performance is robust and the monthly financial return it generates is significantly high, especially when combined with a period of elevated market volatility, then this scenario will undoubtedly be associated with an even more substantial return. It effectively serves to greatly magnify the overall rate of return achieved.
Because the volatility here is really about the variability itself. And when a company like Apple is doing extremely well, that variability will in fact actually increase the overall rate of return.
So we observe two distinct coefficients, each possessing contrasting signs, and this clearly demonstrates the significant importance of conducting the quantile regression analysis.
So to summarize our findings, increased volatility is clearly linked to significantly worse outcomes for the lower tail of returns. For the upper tail, this higher volatility is associated with larger positive returns. That concludes our session for today. Thank you all for listening.